Hello everybody, this is Mr. Strager, and welcome back to Big Ideas, Unit 3. Today we are talking about section 3.3, Function Notation. Now, I'm going to give you some fair warning here. Function notation is all about, well, spoiler alert, notation. It's all about how we write things. We're not actually doing anything new. We're just rewriting things in a certain way. It's going to be a little bit confusing at first, but allow yourself to consider this as a possibility. Here's the deal. Up until this point, we've been using the variables y and x. Specifically, we've been using the equation y equals mx plus b. The reason why we've been doing it this way is because it's very easy to see what our inputs and outputs are. X has always been our input, y has always been our output. However, there's no law saying we have to use these variables. I could have totally written it out as we do in statistics, using completely different looking variables. In statistics, we use this as our variables. We use y with a little hat on it, which is, yes, literally called y hat, equals, we use a to show our y-intercept, so a and b are the same, and instead of m of x, we use b of x. You don't need to memorize this formula, not at all, not at least until you take statistics. But I just want to show you that there are a lot of ways to represent this formula. Things get a little bit complicated, though, when you have a ton of variables. Let's say that you're somebody who takes statistics, and you've only learned the statistics way of writing this, and you look at an equation like this. You could say, I don't know which variables are actually variables, and which ones are supposed to be numbers. Like, what law tells us that m has to be a number? X might be a number, m might be a number. We don't know which is which. I can show you this point even more if I used shapes instead of an equation. If I wrote the equation square equals triangle, circle, plus star, I mean, we could guess what each piece is, but we have no idea what's supposed to be a variable and what's supposed to be filled in with a number. That's why we use function notation. Function notation is a way of writing out this same linear equation, but with a variable that lets us know, hey, here are the two things that are actually variables in the equation. We write it out like this. And bear with me, this is going to look weird. We write down f parentheses x equals mx plus b. So what's the difference between these two? Well, not much, as it turns out. The mx plus b part stays the same. However, we changed out our y for this weird f of x. That's what it's called, by the way. It's called f of x. You can read it as the value of the function at x, or as I will always be calling it, f of x. Y is the same thing as this f of x. Let me be clear about why we're doing this, and then I'll tell you about some common misconceptions with this. The reason why we're doing this is, when we write it like this, we can see what the other variable is supposed to be. Here, we just assume that y and x are our variables. In this form, it tells us, hey, this is going to be your y, and by the way, it's based off of your x. If if I had a complex formula with a bunch of letters, something that looks just absolutely ridiculous, something like Z equals B N J minus 2K. I am clueless about what my variables are supposed to be. But if I rewrote it as f of n equals bnj minus 2k, we can identify what our two variables are. One of your variables is your function notation, so that's going to be our output. And how do we decide what the input is? The input is whatever's inside of parentheses. So in this case, n is our input. By writing it this way, we can communicate a lot more to any observers who aren't familiar with the equations we're using. This is a little bit tough to get adjusted to, especially because it looks like it's saying something else. Let me give you an example. Let's say we had the equation f of x equals, let's call it 2x minus 1. Let's say that we're plugging in a value for x. If x equals 3, let's try to solve this equation. Let's figure out what the value of this output is when x is 3. Normally, if this was in y equals mx plus b form, we would plug 3 in to x and solve for y. Let me write that out for you just so you can see what that would originally look like. So it would look like this. If we just had our y equals mx plus b equation, we would have y equals 2x minus 1. That becomes y equals 2 times 3 minus 1, because as a reminder, x equals 3. And then we would just solve. 2 times 3 is 6, minus 1 is 5. It gets a little bit different when we're writing it out in function notation, and this is the confusing bit. In function notation, we would write it out as follows. We would write out still f of x equals 2x minus 1. And if we're plugging in the number 3 for x, anywhere we see an x, we want to put a 3. So the first x we see is actually in parentheses here. F of 3, in other words, the value of the function at x equals 3 is equal to 2 times 3 minus 1. Keep note, and I want you to star this in your notes. F of 3 does not equal 3f. F of 3 does not mean that we're actually dealing with multiplication here. It means that we're dealing with function notation. It is completely different. So, if you have f of 3, it is not the same as f times 3. It is just f when x is 3. So, when we solve this, we're going to keep on writing it in this form. F of 3 is equal to, and 2 times 3 minus 1, we talked about it before, it's just going to give us our answer of 5. So our final answer is f of 3. In other words, the function when x is 3 has an output of 5. I know, it is a little bit wild, but let's get some practice with it so we can become a little more familiar with it. The most important thing to remember is f of 3 is not 3f. So let's flip to page 72 and take a look at some of the practice problems you might see. Unfortunately, my marker bled through these pages a little bit, but I'll be doing my work on a separate sheet of paper. It says, for exercises 1 through 6, evaluate the function when x equals -4, 0, and 2. What does the word evaluate mean? Evaluate is another way of saying plug in these numbers and see what the results are. In other words, we're given the inputs, use the equation to find the outputs. Here's how we evaluate a function. Let's take a look at number 1. Our original function is f of x equals -x plus 4. What this is telling us is our output is here, and our input is x. So we want to plug in numbers to x to get some numbers out. It wants us to plug in -4, 0, and 2. Let's start off by plugging in -4 everywhere you see an x. Well, there's an x in the first parentheses, and this is just the x that tells us what we're looking at. So now we're saying this is a function when the input is -4. Equals -x, oh, there's another x, so let's plug in another -4. Plus 4. To evaluate, we then just want to simplify this. So, what's -4? Well, two negatives end up making a positive. So, we can say this ends up being 4 plus 4, which we know is 8. So, our final answer is, when we have an input of -4, we have an output of 8. This was when x equals -4. But we don't just want to figure out when x is -4, we also want to figure out when x is 0 and x is 2. So let's try the next part, plugging in x equals 0. So again, our equation is f of x is -x plus 4. So this becomes f of, this time we want to plug in x equals 0, right? I'll use a different color to show this one. F of 0 equals -0 plus 4. Again, we're just plugging in the x's for this first step. Then we start simplifying. The function at 0, in other words, our output when x is 0, is equal to -0 plus 4, which we know is just 4. So, our answer is f of 0, in other words, the function when x is 0 is equal to 4. Let's try just this last one. The last one is plugging in when x equals 2. So, the top one was x equals -4. This one is x equals 0. Let's try x equals 2. Again, we write out the same as before because we're solving these the same way we would if we had y instead. F of 2 is another way of saying the function at 2. We have f of 2 equals, again, we're just plugging in 2 everywhere we see an x. So we had -x plus 4. Now it's -2 plus 4. So when we simplify, f of 2 equals -2 plus 4, which we know -2 plus 4 equals 2. So, at long last, our final answer is that f of 2, our output when x equals 2, is 2. That's how we will evaluate these functions in this section, and in this unit in general. Let's take a look at problem number 7. Problem number 7 is interpreting function notation. So you'll notice that I've been saying out loud what each of the functions means as I've been solving it. Again, the reason why we use function notation is it makes it a little bit more clear what's our input and what's our output. So let's take a look at this. Let n of t be the number of DVDs you have in your collection after t trips to the video store. Whenever you look at a problem like this, the first thing I want you to do is I want you to write down what your input is and what your output is. In this case, what's our input? Well, our input is t. And what does t mean? T is the trips to the video store. We then want to ask what the output is, and the output is usually harder to determine. But as a reminder, your output is just going to be this whole statement, n of t. What does it say n of t is? Let n of t be the number of DVDs you have in your collection. So, number of DVDs. What this is saying is this is a function where trips to the store impacts our number of DVDs. You could say that every time you go to the store, we possibly buy some DVDs, or sell some DVDs, or return some DVDs. Let's take a look at each statement. So here we have n of 0 equals 8, and you have to ask yourself, what's your input, what's your output, what does it mean? Well, our input is t. Instead of n of t, I have n of 0. So that means my input is 0. 0 what? You should always put your units with these type of problems. Well, t is the trips to the video store, so 0 trips is what I'm inputting. My output is the entire statement, n of 0. What does it say n of 0 equals? N of 0 equals 8. So, 0 trips gives us an output of 8 DVDs. So the meaning of this statement is, after 0 trips, I have 8 DVDs. You can interpret this how you will. So I'll say, before I started going to the video store, I had 8 DVDs on my shelf. That's what it means by interpreting the meaning of each statement. After 0 trips, I had 8 DVDs. Or you could write down your interpretation. I never went to the video store, but I got 8 DVDs from my dad. I didn't want to go to the video store, so I cast a spell and summoned 8 DVDs out of thin air. However you want to explain the situation, based off of the inputs and outputs, is up to your creativity, as long as you can determine what it means. Let's try out B. N of 3 equals 14. I want you to try this one out on your own. Pause the video, take a look, and see what we get. Check with my answer in a couple of seconds. Did you figure out the input is 3 trips and the output is 14 DVDs? If not, as a reminder, your input is the number inside of the parentheses. Your output is whatever n of that thing equals. So in this case, an input of 3 trips and 14 DVDs could be interpreted a number of ways. I think the most basic way to interpret it is, I took 3 trips to the DVD store and bought 14 DVDs through that time. C and D are a little bit more difficult. Here, we don't have an equal sign, we have an inequality. And here we've got some nonsense. N of 5 is greater than n of 3. Here, again, let's think about our inputs, this time plural, and our outputs. Here, we don't have much to go off of. We have 2 inputs here, 5 and 3, that we're comparing. So we're saying our input is 5 trips, our other input is 3 trips. Since n of 5 is greater than n of 3, we have to interpret each of these individually. N of 5 means the number of DVDs we have after 5 trips to the video store. N of 3 is the number of DVDs we have after 3 trips to the video store. So we can say number of DVDs after 5 trips is greater than the number of DVDs after 3 trips. And that's basically our interpretation as well. The number of DVDs I had after 5 trips to the video store is more than the number of DVDs I had after 3 trips to the video store. Part D, again, has 2 inputs, but this time they kind of combine to make a single output. This time, we're looking at 7 trips to the store minus 2 trips to the store for our inputs. Our outputs here are the number of DVDs after 7 trips, the number of DVDs after 2 trips. So, number of DVDs after 7 trips is one part. The number of DVDs after 2 trips is the next part. So how do we interpret this? We interpret it just in words. The number of DVDs after 7 trips minus the number of DVDs after 2 trips is 10. What this means is the difference between these two is 10. You could say it then, or explain it as, in between my second and seventh trip, I got 10 more DVDs. That's how we can interpret this one. We got a couple more examples to take a look at before we finish off the notes. Let's go down, keep on chugging along to question number 8. Find the value of x so that the function has the given value. Up here, we were told x equals 4, x equals 0, and x equals 2. In this case, what are they telling us to plug in? They're telling us that b of x equals negative 20. What that means is, since the entire thing, b of x, is negative 20, we have to solve this by plugging in negative 20 wherever we see b of x. This is a little bit trickier to think about, but if you just have a variable they're telling you, plug it into the variable. If they're giving you what the output is, write it in where the output is. So here, we have negative 20 as our output, equals 3x plus 1, and our goal is to solve for x. Well, we've done these before. These are just two-step equations. We did this all the way back in Unit 1. To solve this, we have to think about how to get x by itself. Well, we've got to get rid of this multiplying by 3 and this plus 1. We get rid of the plus 1 first because of reverse PEMDAS. So we subtract 1 from both sides. That'll give us negative 21 equals 3x. How do we get rid of the 3 in front of the x? Well, this is 3 times x, so we would divide both sides by 3. Our final answer is negative 7 equals x. For problems like these, you have to be careful and think, are they asking you to plug in negative 20 where x is, or where b of x is? We always treat b of x, or f of x, or g of x like it's one variable. The very last thing I want to talk about is going to be the last thing we have before our quiz. Questions 12 and 13 ask us to graph a linear function. Now, you might recall some stuff from 8th grade about how to graph linear functions by using the slope and the y-intercept and all that jazz, blah, blah, blah. We're not doing any of that today. That's going to be the rest of Unit 3 after the quiz. So don't stress out about that. Don't stress out about immediately knowing how to graph by looking at a function. We'll get there. For now, we have another tool that we can use to help us graph the function: making a table. In general, And this is the same through all of algebra, as well as all of geometry, algebra 2, pre-calc, calculus, everything. If you have a function that you're having difficulty graphing, using a table is the surefire way to make sure you can get an idea of what the shape will be. Let's take a look at problem number 12. We're asked to graph the linear function s of x equals 1/2 x minus 2. Just as a brief reminder, we usually don't like using the variable s because it looks too much like a 5, so you can yell at Big Ideas for putting that in their book. In here, we have 4 x values, and we want to determine what s of x is at each of these x values. To do that, we do exactly as we did with number 1 in these activities. We just plug in our x values to get out our s of x. So here, we have x equals -4. What that means is we're really trying to find s of -4. What's that going to equal? It's going to equal 1/2 times that -4 minus 2. Since we're not solving on both sides, we're just trying to simplify the equation, we just solve using regular old PEMDAS. A couple of students had asked me, how do we decide? If you're trying to move stuff to another side, then you would use reverse PEMDAS. Here, we're just trying to simplify. So we do 1/2 times -4 first. Well, 1/2 times -4 is -2. We still have our minus 2 here. And what's -2 minus 2? -4. So, s of -4 actually ends up giving us -4. That means when our input is -4, our output is also -4. We won't get this lucky all the time, but that's how we fill in this table. I want you to repeat what we just did with the other numbers here. And yes, it might be a little bit tedious, but I'll give you a hint on how to solve this. Linear functions have a constant rate of change. We'll talk about how to use this information later when we talk about number 13. But try this out first, fill in the table, then try to graph the function. All right, we should have gotten these points for x and s of x. Now it's time to graph. As a reminder, your x values are counted from left to right. Your y values are counted up and down. So if x is -4, we need to look left and right to find -4. -4 is all the way here. So I like to put my pen here so I don't lose where we're looking at, and then I look how much up or down I have to go. Well, if x is -4 and y is -4, that means I start here, and I find y -4 is down here. So this is where my dot's going to go. I like to label my dots as well. You don't need to do this for every graph, but I like to label them so we don't lose track. Next we have x is -2, s of x is -3. So we always look left and right first for our x. Here's x is -2. Since s of x is -3, we count down 1, 2, 3. As a reminder, since s of x is the same as y, we graph it on the y-axis. 0, x is right in the middle. S of x is -2, so it goes right here. 2, -1 ends up being right here. And 4, 0 ends up being there. I'm going to list off a couple of the points just so we can keep track of them. To finish graphing the linear function, once you see the straight line, use a straight edge and actually draw the line through it. A trick to help you solve these is, again, remembering that linear functions have a constant rate of change. You might have noticed that on each of our x points, for each input, we added 2. And for each of our outputs, we added 1. This means if we know something is linear, and if we can determine what the pattern should be, I can use that to fill in the rest. In other words, you only need to figure out 1 point, 1 output. Oh, sorry, 2 outputs, my bad. 2 outputs before you can figure out the rule and apply it to the rest of your points. Let's try using that trick with number 13. Number 13 is t of x equals 1 minus 2x, and we're asked to plug in -2, -1, 0, 1, and 2. I want you to pause the video, try plugging in just -2 and -1, and see if you can use that trick. So this is what we should have gotten when we solved just for -2 and -1. Since we're told it's a linear function, we know that the pattern needs to continue. So we go from 5 to 3. What's the pattern here? Well, we're minusing 2. So to get to the next point, we're just going to keep minusing another 2 to get to 1. If we minus another 2, we get to -1. If we minus another 2, we get to -3. So now we have enough to graph. Again, we start off by looking at our x-axis, -2. Our value of t of x, our output, is 5. So we get -2, 5, -1, 3, 0, 1, 1, -1, and 2, -3. And then we just draw a straight line through those points. Again, you should use a straight edge. Do as I say, not as I do. And we're done. So, thank you so much, everybody. Have a great rest of your day, and I will see you next time.